Hi everyone. The purpose of this demo video is to go over some of the examples that we talked about in the lecture on functions. So let's jump into it. So I have an empty file here, and we're going to first look at some basic functions, specifically the ones from the lecture. So in the lecture we had this completely useless function that just kind of random called b. So all these ones with just single letter names are not meant to be useful, but just to demonstrate a concept. And we're just going to declare it exactly as it was in the lecture. And let's print out one of the result values of it. So I'm just going to say b, and let's call it a 3, just like we did in the example in the video. So let's run this. And you can see that it prints out b3 is equal to 5, and that should make sense. Let's quickly trace it. So we're passing in 3. The 3 gets copied into this x argument here, which is a local variable. It's going to be added to the calling stack, by the way. And so we have a value of variable x which equals to 3. And then it's going to create a local variable called y, which is equal to 2. And then we return x plus y, which is 3 plus 2. Okay, so it's going to return 5, which is why we get 5. Now, if you're not sure why that works, what you can do is you can set a breakpoint. This is what we talked about before when we were using the debugger. But now that we're doing functions, using the debugger has a few more features because you can go into and out of functions. So, for instance, I've just set a breakpoint next to the print statement here. It doesn't, actually, let's set a breakpoint here. Let's actually watch what happens. I'm going to go into here. I'm going to pick debug. So make sure in the drop-down box you're picking debug. It changes the icon to a play button with a bug. Okay, when it finally gets to this line of code, you can see we got all of our debug panels open here. We don't really have any useful variables right now, but let's step over this program, this function right now, and you can see that it's just going to define the b. So if we open up this function variables, you'll actually see that we have this variable v now, and it's a function, and it'll tell us the address and all that stuff if we care. I don't know why we'd want to know the address, but it's a big gigantic hexadecimal number. It's the location in memory where we'd find the code for that function, but we don't really need to know that, so I'm going to ignore that. So now you can see that the code control is returned right here. And so we've been using this button right here, which is the step over button. If I use that, it's just going to skip over the whole thing and just run the whole function and then produce the output. Oh, no, it's not. I was wrong about that. Most of the time, that's what happens in a debugger. Usually when you have step over, it jumps over the function call. But this one actually jumps into the function call. But there are specific buttons for that. There's actually step into, which when you're on a line of code that calls a function, it's going to go into the function. And then there's also step out. So if I click step out right now, it would actually leave this function and go back to this line of code and finish executing this line of code. Okay, so I'm going to not click that one. Let's actually step through this program a little bit at a time. So you can see anyway, on the very first line, just like in the animations, we have a local variable called x, which has the value 3. This is just showing you basically how this was working before. You'll also notice that there is a calling stack, just like we were talking about and I showed you in the video. You can see it just calls the bottom stack frame the module, which basically what it calls this global code that's not inside a function. But then on top of that, you can see that there's a stack frame specifically for b, the b function. Okay, so now I can step through this program. So for example, I'll do step over, and then step over one more time. We'll create the y local variable. See, we've got x and y now, and then step over one more time, we'll compute the result. And we can also use this step out, which in this case, it'll do the exact same thing. Step out only does something different if you do it at not the last line, right? Here we're at the return statement. This is going to be the last thing that this function does. So either this button, or even this button probably will do the same thing. They'll bring us back to this line 8 using our return address that's found in the calling stack to figure out where we should go back. Okay, so it prints out 5, and that's the end of the program, so nothing super interesting there. All right, so I'll close this breakpoint down. I just use the mouse here. You can see there's a little ghosted red button, and if you click it, it becomes brighter. All right, so another example that we did was to create two functions where one function calls the other. So we've already got the b function here. So let's just define the a function now. There was an a function which had an argument z, and it created a variable x, a local variable x, which is equal to 1. It also created a local variable y, which was equal to the result of calling b with the argument z being passed. So the a function is calling the b function. So this will give us a chance to trace the execution of this function. And it just returns y minus x. So let's test this out. I'm just going to do, even it doesn't even matter what the value is right now. I can literally just call a3, just maybe for clarity to show what's going on. So what I'm going to do is I'm going to set a breakpoint right here. I'm going to save my program just in case. I always like to make sure I keep on saving. And I'm going to run it up until that breakpoint. Okay. And if I open up function variables here, you can see that it already loaded both of these functions. It hasn't executed them, but somewhere in memory there's a b function, and somewhere in memory there's an a function. And now I'm on this line 15 here. And you can see that the calling stack only has module, which means we're only running the global code. We're not inside a function right now. And so all I'm going to do is I'm going to push this step into button, which is going to go into the a function. Okay, so when I click on that, it goes into the a function. And you can see now that it copied the value of the z variable, of this 3 rather, into the z argument. And it's a local variable. Now we have an x variable. Let's just make that happen. You can see that we've got this x here. But now we're about to call another function. So I kind of have a choice here. Do I just skip over and let that function call happen? Like imagine I'm calling a built-in function like square root or len. I don't really care. I don't want to see that execution. I want to continue with my code and examine my code because I'm trying to find a bug, let's say. I know the bug's in my code. It's not in the built-in len function or the square root function. So in this case, I want to jump into this function because this is one of my functions. But you might not want to if it's a built-in function. So I'm going to click on step into to force the issue, and it steps into the b function. Take a look at the calling stack. We have module on the bottom. That's the global code. And then the first function call that was made was a. But the current function, which is the one that's highlighted here, the currently executing function is b. That's the one that's on the top of the stack. So the top of the stack represents the currently executing function. And that's where these local variables are stored. Okay, so when this function exits, these local variables go away because they're actually inside this b stack frame here. And the b stack frame gets deallocated from the stack. Okay, so we'll step over this and create the y variable. And now if we do step over, or we could do step out. Let's do step out. And that's going to compute x plus y and return that value. So that's going to send us back to this line of code here. And so now we know that this value is 5. You can see that the calling stack is a little different. We don't have the b stack frame anymore. We just have the a. A's on top now, and you can see it's highlighted because that's the currently executing function. So let's step over this line of code now. It's going to set y equal to 5. Okay, so you can see we've got all 3 of these variables now. And now we can compute y minus x. So y minus x is 5 minus 1, 4. So when I click on this, either step over or step out, it's going to go back to the function call originally. And now it knows that the return value for this function was 4, or 5 minus 1. And I didn't print it or anything, so it doesn't do anything down at the bottom of the screen. All right, so there we go. So that's how to use the debugger to trace your program. I'll probably do that for some of the recursive examples a little bit later. Let's turn this into a print function so it's a little easier to follow in the future. Okay, now we can just run it in the non-debug mode and still see the output. So that looks good. Let's kill this breakpoint as well. All right, so remember that there are 2 ways to pass arguments in Python. One way is passed by value, and this is used for all small types, especially numbers, booleans, etc. So we had a function in the slides that was called getAge in dog years, and we passed in a human age variable. Okay, and the function just returns human age times 7, so pretty straightforward. And so what's happening in this case when I call this function, for example, if I call the function inside an F string, why not? We could just say something like, get age in dog years of, let's say, 3. it's going to copy this 3 into human age. Well, even if it's a variable, so I could say something like dog age is equal to 3. And then over here, instead of putting the hard-coded 3, I can put dog age in here. Now I have a global variable called dog age, and I'm copying the 3 from that global variable into the human age variable. Okay, so these are two different, oops, I forgot to put the equal sign in there. These are two different variables in two different locations in memory. Now I haven't tried to change the variable here in any way, but let's use a different function for that. This doesn't really make sense for this particular function. All right, so let's define a function. I'm going to call this try to set arg. Okay, and then let's pass in an age variable, let's say. And all I'm going to do is I'm going to try to set age to something else. Okay, so let's have our dog age variable. Let's just make sure that it's 3. Okay, and all I'm going to do is I'm going to call try to set arg with dog age. So I'm passing dog age into this function, and the function is supposed to change age to 8. You can actually see there's a little bit of a hint here provided by Visual Studio. It kind of grays it out to show you, oh, this isn't really going to do anything. But anyway, spoiler alert, Visual Studio wants to tell us. So let's just put in some code. We'll say something like after executing, try to set arg. And then we'll just print out the dog age variable. Let's see what it looks like. So not too surprisingly, dog age still has the original value 3, because again, pass by value means these are two separate variables. So dog age is a global variable. It has the value 3. We copy that 3 into this local variable age. We do change the local variable age to 8, but then we quit the application, and this age being a local variable, it's stored in the stack frame. And once we exit the function, the stack frame goes away. So that variable just disappears. So that 8 is really gone. So it is the case sometimes that we do actually want pass by reference. Now there are some programming languages that let you choose when to use pass by reference and pass by value. So for example, in C++, if I pass in an argument like a to a function, let's say I call a function b, let's say I call the function b with the variable z, that's going to pass this z in as a pass by value. And if I pass it in with an ampersand, then it says pass in the same z variable, but I want you to pass it by reference. But you can't do that in Python. With Python, it's chosen for you based on the type of the value that you want to have. So what I'm going to do, before I do that, I actually wanted to show you, I'll just do it on a few of these, I suppose. I wanted to show you how to add type hints to your function. So we'll come back to we'll come back to that after we do pass by reference. So first of all, I'm going to create a function that specifically changes its argument. Okay, so let's create a function called remove first. It takes an lm's argument, and then what it does is it says lm's.pop 0, let's say. So that's literally going to remove the first element. So let's try to do that. So let's, for example, set a set of names, let's say, and let's put in 3 names. Okay, so let's put in the professor, and then I'm just going to call remove first on names, and then I'm going to print names. Okay, so in this case, because this is passed by reference, because it's a list, lists are usually big, and it's very inefficient to make a copy of a list. This list could have 1 million elements in it. This one doesn't, but generally speaking, lists can be very big, and you can have lists of dictionaries, so there's a lot of data there. So when you have dictionaries and when you have lists, Python by default uses pass by reference. That means when I pass in this names list here, this gets passed in as the argument to remove first. This lm's here is just another name for the same space in memory. So lm's and names both point to the same location. This is a local variable that points to that memory location, and names is a global variable that points to that same memory location. After the local variable goes away, the names still exist because the global variable still points to them. Okay, so this will actually remove the name, as you can see here. In this case, Fry is missing from the list. All right. All right, so now that we've talked about pass by value and pass by reference, let's talk about how you can add type hints. So Python is a dynamically typed language. That means, generally speaking, your variables can take on different types. Even at different times, they can evolve and take on different types. But generally speaking, it's considered a good practice to be consistent about your typing. There are some places where you can take advantage of it. So, for example, some operators work on string, like the plus operator can concatenate two strings together, but could also add two numbers together. And in that case, leaving the types vague actually is a benefit to us, because we can use the plus operator, or we could write a function that uses the plus operator on its arguments and not define the types. But sometimes, in fact most of the time, we do want to specify the type hints. And I'll give you an example of why that might be. But for instance, let's say I want to take this function, and this function takes a single argument and it returns a value. So let's try to specify what the types are. So after the argument name, I just do int, int. And now it says, oh, okay, so this argument here is supposed to be an integer. Okay? And so now down here, I'm not going to keep this code, but I'll just type in dog age in, get age. Sorry, that's why it wasn't working. Get age in dog years. And when I type in the round bracket here, it gives me some clues now, and it says, oh, look at this. I think this should be an int. And it also says this is what the return value should be. Now that it knows what kind of value human age is, it's also able to figure out, since human age is an int and I'm multiplying it by an int, 7, then the result should also be an int. So it's able to infer some types from this. And if I take out this type hint here, it might not have been able to do that, because human age could be like a string or whatever. So it says, oh, that could be any type, and the result could be any type. Like, I don't know, maybe there's some way to, multiply something. Like if this was a string, I could multiply it by 7 to, replicate the string. So putting this type int actually means that the autocomplete, or the hints in the editor are more valuable. If you want to provide a hint for the return value, what you do is you put a little arrow, which is like a dash greater than, and then the type. So this is showing you what the output type is. I didn't need to do this because Python was able to infer, but for completeness here, I'm going to specify all the types for a few functions here. So in this case, you actually will see, oops, I left that code in there. You'll see that it works the same way as it did before. So there's nothing new about how the function works. But now it's going to give me those type hints. Now you might be wondering, okay, is it going to be enforced? Like, could I call get age in dog years with a string, for instance? Like, for example, if I pass in the string dog, let's actually print that. So I'm going to need double quotes here. Okay, let's see what this does. So you actually see that it still works with strings. So we have said that this is an int. So this is important if you know an existing programming language like C++ or C or Java. Those are not type hints. Those are actual declarations. You're saying that this argument has to be this type. In Python, we're just making a suggestion to the person using our code saying, I've tested this code and I mean for it to be used with integers. It could work with non-integers. As you can see in this case, this one does work with strings. Okay, so it is possible. Okay, I am going to remove that just because, it's bad practice, generally speaking. We should respect the type hints. Mainly because, we can't guarantee that this code is always going to work properly. If the type hints are there, that means whoever wrote that function meant for it to be used with those types. That means they fully tested it with those types, but they didn't necessarily fully test it with other types. Okay, let's quickly type try to set arg here. That takes an age, which I would also expect to be an int, so we can put :int for that. And the return type here, we don't return anything. So we're going to put arrow, and I'm going to put none, capital N, none. That's the type when you don't return anything. So that is has set the type of that function properly. you know what, maybe we should just go through all of the functions here. So in this case, the A function takes an int argument, and it also returns an int argument. So I'm going to do arrow int. And same here, the B function's first argument is an int, and it also returns an int. There's a lot of int functions here, sorry about that. We'll vary it a little bit later. Okay. Remove first. LMs is actually a list. So I could just literally put a list. And you can see in this case that I specifically am using it with a list of strings. So a list is not wrong. It's fine. I could also put a list square bracket str, which indicates this is a list of strings. So that'll help it work with this list specifically. Now, all three of them worked when I didn't have the type. And this, by the way, also returns none because it doesn't have any return. It just changes the list that's the argument, so there's no reason to return anything. You see that it works. But also, if I get rid of this square bracket str and I just say it's a list of any kind, it also works. And you'll also find that it works with lists of integers and lists of booleans and stuff as well. But it also works, without any of this. So just leave it. I don't put a type hint for that variable at all. It still works. I think I'll leave the str in there just to show you how it works, but please note that you can also leave out the type of the string. Okay, so that's all of the functions that we've got. So now let's talk about named arguments. Let's say we should call this, arguments. Let's call them keyword arguments. I think that's the official name in the Python documentation. So whenever I declare a new function, let's say, for example, I create a distance function, and I do something like x1, y1, x2, y2, and let's say, for instance, I return, and I'm going to have to import math. I like to do my imports up at the top. I'm going to need the square root function, which is in the math library. So to use that function, I'm going to have to do an import math up at the top. So I'm going to return math.squareroot. And it's the square root of the difference in x value squared plus the difference in y value squared. So I'm going to say x2 minus y, x1 rather, squared. I can use the exponent operator, plus y2 minus y1 squared. And the whole thing gets square rooted. So there's our distance function. This is Euclidean distance, and if you think about it, it's basically Pythagoras being used here. And so this is actually pretty helpful because I can do something like this. I can say distance, then I can pass it in some values. So let's say, for example, I want to find what's the distance between the position 0, 0 and the position 3, 4. Okay, so let's put the equal sign in there so that I can see these arguments. And that tells me the distance. That's great. So it looks like the distance is 5. That's useful. But like the order here, it's not clear like which arguments are which, right? Like unless I go back and actually look at the function, it's a little unclear what these are. Now the distance function does give me some hints. Like if I hit the bracket key here, you can see that it shows me. It doesn't show me any types right now, but it does actually give me the names of the arguments, which is helpful. So we're trying to make it as easy as possible for people to use our code. And so one of the things that we can do is we can call this function by specifying the arguments using x1. So for example, if I want to set x1 equal to 0 and y1 also equal to 0 and x2 equal to 3 and y2 equal to 3, I'm calling the same function with the same arguments, but now what I'm doing is a way that's a little bit more readable because I know x1, y1 are 0, 0. Like maybe I put x1, x2, y1, y2. In that case, this function here is going to be very different, whereas this one over here would still work. So you can reorder the arguments if you want to. They don't have to be in the original order. First of all, first things first, let's print this out to the console. Okay, so we'll just print this out to the console just to make sure that the value is still the same. Like it prints out a different message here, but you can see, whoops, I put 3, 3, 3, 4. it should be the same if you put in the same values. There we go. So we still get 5 and 5. And you actually will notice that even if I reorder some of these, let's actually reorder them. Let's put the x values first and then the y values. It still works. Even though, that if I didn't use named arguments and I just put 0, 3, 0, 4, that would compute a very different value. So that's a distance of only 1, not 5. And so that's going to be very different. Okay, and then let's go a little bit further and let's make sure that we type all of these. So let's set this to float and float and float. It would make sense that they're float, I think. They don't have to be integers. So now when I type in distance, it gives me all the clues that I possibly can. It's got named arguments, and it's got types, it's got return type as well. So this is as easy to use as possible, especially considering I used a pretty straightforward name. Another thing you can do with arguments is you can have default values. So let's create a function that has a couple of arguments. Let's say I create a function called calculate interest, and it has a principal amount. And why not? Let's actually declare it as a float now. We'll bother to add the types in after. And then we'll have another one, interest rate, and we'll call that a float as well. And then why not? I know the result's going to be a float, so let's declare the return type as a float. And I'm just going to return principal times interest rate as the code of this function. So it's pretty easy. It's just calculating the interest content. So that's pretty helpful. So I can actually down here, I can call calculate interest, and I just have to pass the values to it. So for example, I could say a principal value of, say, $5,000 and an interest rate of 0.025 or 2.5%. So this will work. But it may be the case that I don't want to always specify all the parameters. So for example, when I'm making the videos for this class, I often have a default font size and a default color to be used for some of the text in the animations. The animations, by the way, for this class are done using the Manum library, which is a Python library. So I write code in order to generate those animations. And a lot of the functions that I end up writing have default values. So it saves me typing them if I'm just using the default function, the default font size or the default color. So this is actually something that I can do. So this works fine. It says, okay, the interest on 2.5% of $5,000 is $125. That's fine. But what if I want to set a principal value? So all you have to do is after the type, you just have to specify what the default is. So maybe I want the default principal amount to be 1,000. I don't know if that necessarily makes any sense to have a default principal amount, but maybe a default interest rate might make sense. Maybe this is our rate that we're offering our general customers, and then some fancy customer comes in, a really good customer of ours, maybe we can give them a slightly better interest rate. So what this allows us to do is we can call calculate interest now in different ways. So for instance, if I would prefer to specify these using the keyword arguments, so I'll do principal is 5,000 and we'll do interest rate is equal to that. So that's specifying all of the parameters. That should work the same way as just using the positional form of passing in the arguments. So the result's the same. But now I can leave out some of these values. So for example, if I leave out the principal, only specify the interest rate, and the interest rate is different than the default. So in this case, you can see that we end up getting a different amount because this is calculating on the 1,000 principal, the default amount. And we can also pass in a principal amount and then just use the default. So in this case, maybe put 5,000 for the principal. Use the default interest rate. Okay. And funnily enough, I can even call the function without any arguments at all, because in this case, they all have default values. So I can just call calculate interest. I don't know if this necessarily makes sense for these to have defaults. You'll only put defaults if it makes sense, right? If you can figure out a sensible value to use, If the person calling your function doesn't provide a value, then go ahead and do it. So in this case, I don't think principal really is appropriate for that. I don't know if I mentioned this in previous lecture, but you'll notice down here that there's kind of a calculation error. We're going to address this in a future course, but this just has to do with how computers store floating point values. They're not super precise, so there's certain kinds of calculations that require lots of digits, or when we compute things, we tend to round off or go to a certain number of decimal places. But Python tries to remember as many digits as it can. Sometimes it doesn't have enough digits to represent. We might need infinite digits, or we might just need more than we have, and it does these little floating point errors. You can see here that the correct result is supposed to be 175, but we ended up getting 175 and a tiny bit more. Okay, so let's move on to recursion then, which is a bit more of a complicated topic, so this is going to require a lot of practice. So let's write the Fibonacci example that I introduced in the slides. So the Fibonacci sequence, as you may know, is 0 and then 1, and then all the subsequent Fibonacci numbers after that are the sum of the previous two. So add up these two, we get 1. Add up these two, we get 2. Add up these two, we get 3. Add up these two, we get 5. Add these two, we get 8, and so on. Okay, so this is an infinite sequence of numbers. They're non-negative integers. And the definition of Fibonacci is literally that the Fibonacci of 0 is 0. The Fibonacci of 1 is 1. In other words, just like I was describing it, the first two numbers are 0 and 1 in the sequence. And then for all others, the Fibonacci of any n is equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. In other words, the previous two. And this is if n is greater than 1. And another way to write these two things is to say that the Fibonacci of n is equal to n if n is equal to 0 or n is equal to 1, right? So I can get rid of that and combine these together into a single line. And this is the mathematical definition. I'll use the big curly bracket kind of notation, but basically that's how I'm going to write the code. I'm just going to say, well, if the n value is less than or equal to 1, then I just return n, because it's either 0 or 1, and therefore the value is either 0 or 1. And otherwise, I'm going to return the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So this is a complete, albeit very inefficient, complete implementation of Fibonacci. It's recursive, so the function calls itself, and this is perhaps the most complicated recursive function that we'll deal with right now, but obviously there's a lot that you can do with recursive functions. So just for the sake of it, let's actually call Fibonacci with the n value of 8, just to make sure it calculates the correct values. So when I run it, I end up getting 21. Let's just double check. So this is 0, 1, 2, 3, 4, 5, 6. So let's calculate 2 more. So 5 plus 8 gives us 13, and then 8 plus 13 gives us 21. So it looks like we're calculating the correct value. Oops, sorry, that's supposed to be dot dot. Okay, here's where Fibonacci goes wrong. If I want to calculate, now it didn't take me that long to do these 9 Fibonacci numbers. I could keep on going and the math would get a little harder, but if I had a calculator handy or whatever, it would be pretty easy to calculate the 40th Fibonacci number. But I will just say that a computer will really struggle with calculating the 40th Fibonacci number. So you can see there's a significant delay. And if I wanted to calculate, say, the 100th Fibonacci number, I don't think my computer would ever do that. I think my computer would be long destroyed by the time it calculated, because this is a very inefficient algorithm. But it is simple, and that's a general rule that you'll find is sometimes when you're solving a problem, it seems counterintuitive perhaps, as as a computer science student just learning coding for the first time that recursion is the easy way, but believe it or not, it is. It's the easy way to solve certain problems, especially like binary tree operations. A lot of algorithms are often implemented using recursion. Quicksort is a common algorithm that's typically written using recursion. But then for efficiency, you might try to avoid using recursion and then turn it into a non-recursive function or iterative version. And then that actually requires a little more thought. So it takes a little longer. It's a little harder for you to do that. Okay. So anyway, that was the example. I think we did a few other functions. So here's another one. Print n times. Took an n value. Let's put some types in there. So n value is an integer. It also took a message, which was a string, and that returns nothing. And all it does is it says, well, if n is equal to 0, then just return, like you're done. If it isn't, then we'll print message. And then we're going to do the recursive call. All right, now, the recursive call, it's important. If I just do n and message, then I have infinite recursion, even though it seems like I have a base case here. I don't really, because in this case, this n value never changes. So this call to print n times and the next call to print n times have the same n value. And I'm using the n value to see when I exit. If I never change the n value, if it's not equal to 0 at the beginning, it's never going to be equal to 0. So it's extremely important when you're doing recursion. You got to watch out here. You got to do something to the value that you're using to check. So it's the combination of this if statement here and the fact that I'm changing the n value in the recursive call that actually functions as the exit condition for this code. Okay, so this will actually print the message n times. Let's give it a quick try. Let's print 5 times. Hello, programmers. Here we go. Prints 5 times using recursion. Of course, I can implement this using loops very easily. All right, so if you remember from the lecture, we talked about a special kind of recursion called tail recursion. And tail recursion is defined as the kind of recursion that happens when the function call, the recursive function call, is literally the last thing to happen chronologically in the function. And this is an example of tail recursion, so let's label it accordingly. And the reason why it is, if you look at the code, the only recursive call is at the very end of the function, and nothing else is going to happen after this call to the function. And what that basically means is that I don't need any of the variables that were declared. I never need to come back to this line 82 ever again. I could just go back to line 84 where the function was called eventually. All I really need to do is repeat the correct number of times. So I can save a lot of memory and avoid the stack by doing that. Okay, if, by the way, you want to see why Fibonacci is so inefficient, what I would suggest is try that Fibonacci of 40, run it in the debugger, and trace through all the different calls. You'll see that it generates this big gigantic tree of calls. Fibonacci of 40 calculates Fibonacci of 39 and also Fibonacci of 38. Well, Fibonacci of 39 calculates Fibonacci 38 again, and also Fibonacci 37. So it creates this big tree with a lot of redundant calculations, and all those redundant calculations mean that this algorithm can't really be used in practice. But it's simple, and it's a good exercise for people just learning how to program. Okay, so let's put in a little message that says this is tail recursive. So this will be optimized by Python automatically for us. But it's also kind of a clue that, maybe we should consider making this a loop, because usually if it's tail recursive, it's usually pretty straightforward to convert it into a loop. All right, the other function that we considered in the slides was this one. It was a function that adds up elements in a list, and we should actually declare the types here. So this would be an int. It could be an int of a list rather. It could be a list of int, which is how I'm testing it, but I'm just going to leave it as list. Okay, so it could be something like list of float or list of int. That would work fine, but I'm just going to leave that out. And then in this case, you know what? Actually, let's make it list of int. Why not? That way we can also declare the return type to be list, because to be int. Because if we have you know, a list of integers, then the sum is going to be an integer. If we have a list of floats, then the sum would be floats. Just for completeness, I want to put more type hints in here to give people more practice, but obviously we don't need to do that. If I was writing this in reality, I think what I would do is I would just declare it as a list, and I wouldn't specify the return type. All right, so all I'm going to do in this case is I'm just going to check to see if the LMs list is 0. And if it is, I'm just going to return 0, because the sum of a 0 element list is 0. Then we're going to calculate the sum. So what we're going to do, basically, the algorithm here is that I want to take the first element of the list and add it to whatever the sum of the rest of the list is. So I'm going to use recursion to calculate the sum of the rest of the list. That's what we're doing on this line here, line 90. And then I'm going to add it to the first element on the next line. So I'm literally going to call the function I'm currently working on, SumList, and I'm going to pass it LMs. But instead of LMs by itself, which would be infinite recursion, I'm removing one element from the list. And if you remember your slice operator, this says everything in LMs except for the first element, index 0. Okay, so this is going to call SumList again with one less element. And since I'm removing elements every time I make the recursive call, and I'm exiting when the length of the list gets small enough, I guess if you're really worried about it, you could say if it's less than or equal to 0, like it's not possible for the element to have less than 0 elements in it, which is why I didn't do that. But sometimes you can put a little safety code in there if, for example, you're working with an integer rather than a list. So then all we're going to do is we're going to return LMs at position 0 plus some rest. Okay. All right, so let's think about this. Is this a tail recursive function? And I think it's pretty clear that it's not, right? Because the recursive call is on this line here, and then there's this code. But there's actually a lot happening after. So first of all, after we do the recursive call, we then take that value and put it into a brand new variable. So we're creating a new variable, SumRest. And then we add the two values together, and then we return that. So like even if I were to, for example, change this program so that instead of creating that variable, I did this kind of appears like it maybe is tail recursion, but it's not. Because even though like the last thing to happen in the function, like the last text in the function is literally the function call, it's not the last thing to happen chronologically, because I'm going to calculate the sum of the rest of the list, and then only then can I add these two things together. So the addition is the last thing to happen here, and the return after that, in fact. So this is not tail recursive. But does that mean that it's not possible to implement the SumList as a tail recursive function? Well, it actually is. So let's do that. So I'm going to call this SumList tail, and that takes a list of elements, and I'll pass in the type. I'm also going to add a second argument to this. And the reason why is the argument is what's going to hold the sum for me. So the way that this SumList function works is it goes down into the recursive and it calculates the sum of a really small list, like an empty list. And then it works its way out by adding the one element that was removed to that sum. And then it goes back out and adds the one element that was removed to that sum, and so on. So it kind of goes deep into the recursion, and it calculates the sum on the way out. What I'm going to do is I'm going to calculate the sum on the way down into the recursion. So I'm going to have a function called base. Okay, and this is going to be an int, let's say. And all I'm going to do is say that the default value of base is going to be 0. And this is going to be an int function, like SumList was. So I still need to have an exit condition, so I'm still going to use the exact same exit condition. I'm just going to say, well, if the list is empty, then that means I just want to return base, whatever base is. Okay, so base is initially 0, so it's going to return 0 just like the original function would if the list that we passed in as the argument was empty. So that's not going to change the functionality of the code. But it's important that this is base and not 0, because this is actually going to be the only actual value that we returned. So if I only ever return 0, I'm only ever going to get 0 as my output. So let's try to figure out how I could do this. So what I'm actually going to do is I'm going to compute the first element plus the base on the way down. Okay, so base is initially 0, so adding base to something isn't going to change it. So it's basically going to be equal to the sum of the first element by itself, just the first element. But then the recursive call is going to take the new first element and add it to the old base, which was the old first element. So it's going to add those two elements together. And basically, as it removes element from the list, it's automatically going to add it to the base argument of the recursive call. So I'm basically going to do SUMList tail. I'm going to go to LMs. Of course, I'm going to remove the first element from LMs. But then for the base value, I'm going to take whatever the old base value was and add to it the first element of LMs. Okay? And so now you can see that SUMList tail actually is the very last thing to happen in this function. There's no adding or anything like that. And by the way, this is allowed if I return the value of this function call. That's actually allowed, and it doesn't make it not tail recursive, because returning is the very last thing that all functions automatically do anyway. And even this function right here doesn't have an explicit return, but it does return after it calls this function. So that code is kind of implied as part of the code. So this is a tail recursive version of the exact same code. And they should both work, so let's just quickly test them both. So I'm going to do print, we'll do SUMList first. And let's do something like, 1, 2, 3. And then what we'll do is we'll call the SUMList tail function with the same exact list. And just make sure that they both seem to work perfectly. They do. And if I were to compute like a huge list, I could do that, I guess. So let's just copy these. So let's say SUMList, instead of passing it a list, I know I'm supposed to pass it a list. I could actually use the range function. So I could do something like 1,000,000. So sum all the numbers from 1 to 1,000,000. Let's do that for both. And let's see how that goes. That's going to take a little while. And I think that we won't be able to do it because this is going to be recursion depth limit exceeded. Yeah, because if you think about the way this works, like the idea is sound, and it would work on a programming language that doesn't have this limit in place. But it would be a very bad idea. It's not a very efficient way to calculate the sum of a list of 1,000,000 numbers. Because every single time I take one value off the list, and then I recursively sum the rest of the list. So this is going to make 1,000,000 calls to SUMList and SUMList tail. And so that's using up a huge amount of stack space. It's going to create a stack frame for every one of those 1,000,000 calls. So that's why this doesn't work. There is a limit to how many times you can see, and I think it's something like 1,000. So you can see that it prints a line a couple times, and then it says, oh, and 995 more of that same thing again. And you can see it's just a whole bunch of the same line over and over and over again. Okay, and so if I were to reduce this down to something like 900, something a little bit more reasonable, we'd see that these two functions would do this quite quickly. Like we wouldn't even be able to tell the difference speed-wise. But memory-wise, there is a big difference in how the SUMList tail function would actually work. Anyway, so that's all for this. It's just meant to give you a little bit more practice. Make sure that you do a lot of practice with recursion. I know the recursion can be intimidating, but here's the trick. Do it wrong on purpose, mess around with it on purpose. For example, that infinite recursion function that we did, type it out, run it in Visual Studio Code. If you end up getting in a situation where it truly is stuck, that won't happen in this case because of the recursion depth that Python enforces. then just hit Control-C down here in the terminal, and it'll quit the program. I had to do that once today for, I forget what, I forget what I was doing, but anyway, I had to do that already. So you see, I just use Control-C, and that quits. So you can always do that. It's no big deal. Don't be afraid of what that kind of thing that can happen, because it is important for you to recognize when that happens by accident in the future. If it happens by accident, then you will recognize it, and then you'll know exactly what the problem is, because you've experienced it before. And in fact, you did it on purpose before, so you know what to change to fix it. And then secondly, practice, practice, practice. That's the only way to get recursion. Eventually, like, it's confusing at first because you have this kind of magic box. You're implementing a function by saying, use the function that I'm currently writing. So it's sort of like you have a recipe for pizza and it says, step 1, make a pizza. So that's not a very helpful recipe, but believe it or not, it is possible to create a recursive function, because each recursive call is doing only a smaller part of the problem. So the current call to the recursive function is solving a big problem, and then the recursive call is solving some smaller version of that problem. And each recursive call is solving a smaller and smaller and smaller version of that problem, until eventually the problem is so small you don't need recursion to solve it anymore, and that's where the base case comes in. So in this case, for example, here's the base case, but you can see that we're calling SumListTail to do a smaller calculation. We're asking it to sum a list again, but this list is smaller, so it's one less element, and so it actually is significantly easier to solve. And eventually, we take one step at a time, we eventually get the list so that it's empty, and we can definitely solve an empty list, the sum of an empty list. Okay, anyway, so that's all for today. See you next time.